Alright, let's go ahead and prove that f is differentiable at 0 for part A with this whatever function we're given. So what we're going to do is we're going to compute the limit that would have to be equal to 0 if the derivative were 0, and we're going to find that the limit is 0, which means that the derivative is 0, which means that it's differentiable. Okay, so, but before we get to that, we need to do, and this is something we're going to do in a lot of these. In a lot of these limits, we need to use the squeeze theorem. So for any real number h which is not 0, sine of 1 over h is, well, sine can be between -1 and 1. So that's going to be like this. So we take this inequality and we do this. And this holds for, okay, I just realized something. This holds if h is positive. If h happens to be negative, then you have to flip all of the inequalities, but you have to flip all the inequalities, but you also have to have minus signs, and so it ends up being the same exact thing. So don't worry about it, I guess. Okay. And so if we take this inequality and we take the limit as h goes to 0, then on the left and the right we'll get 0, and on the inside we'll just have the limit as h goes to 0 of h times sine of 1 over h. And so therefore, by the squeeze theorem, it must be the case that the limit as h goes to 0 of h times sine of 1 over h equals 0. So here, I guess, like, if you wanted to avoid that inequality thing, you could have done, like, this, you could have used absolute values here if you wanted to, but I won't worry about it too much. It's really not a big deal. So therefore, if we want to compute f prime of 0, well, let's start on the next line. F prime of 0 yes, because this is the one-dimensional case, we're able to just go straight ahead and compute this limit. If we were in the multi-dimensional case, we would have to like do something a little fancier, because you can't just like, you can't obtain the derivative just by taking a limit. You have to, the derivative needs to be some function such that some limit exists. But here, because we're in the one-dimensional case, we don't have to worry about that. So we take f of h minus f of 0. So limit as h goes to 0. You still have the 1 over h. And now f of h is just h squared sine of 1 over h, because h is non-zero since we're taking the limit. And then f of 0 is, well, 0. So we have this. So then this is the limit as h goes to 0 of h times sine of 1 over h. Well, look at this. We just proved that this is 0. So f prime of 0 is precisely 0. So f is differentiable at 0. However, if we take x not equal to 0, we can actually compute f prime of x, which is going to be the derivative with respect to x squared times sine of 1 over x. This is going to be, we just use the product rule, 2x times sine of 1 over x plus x squared cosine 1 over x times, now we take the derivative of the inside by the chain rule, and so the derivative of 1 over x, that's the same as the derivative of x to the minus 1, so you bring down the minus 1 and decrease the exponent by 1, so it's minus x to the minus 2, and this will have some cancellation here. the sine of 2x sine of 1 over x will stay. Then we'll get minus cosine of 1 over x. So the limit as x goes to 0 of f prime of x, well, the 2x sine of 1 over x, you can use the squeeze theorem to prove that will go to 0, but cosine of 1 over x, that limit will not exist, because as x goes to 0, this oscillates more and more. So this limit does not exist because the limit as x goes to infinity of cosine of x does not exist. So this limit does not exist. So f prime is not continuous at 0, which is odd given the fact that it's differentiable there. But yeah, differentiable does not imply continuously differentiable, and this is just an example of that. Alright, so we have this. And now we do part B, which is essentially the same function, but it's sort of like if you were to take this function here, it's like if you took xy and you took the norm of that vector. You take the norm of this vector and you plug it into the function f from part A, and that's essentially what f in part B is. Okay. So here, in order to prove that this limit exists, now we have to do that thing that I mentioned at the beginning, where we have to, instead of doing it directly, we have to prove that we have to show that a particular limit does exist, and that implies something about what the derivative actually is. So we have to do a similar squeeze theorem type thing. So for all vectors h and k are in R. So for each vector hk in R2, which is non-zero, we have 0 is less than or equal to, and now we're using absolute values. Sine of 1 over the norm of hk is less than or equal to 1. So 0 is less than or equal to norm of hk times, well, yeah, we're just multiplying this by the norm of hk, sine of 1 over the norm of hk, which is less than or equal to hk. And so if we take the limit as hk, I'm just going to write this as the limit as h and k both approach 0. We take this vector times sine 1 over norm hk. Do I have enough room here? Yes! Okay, so this is 0 by the squeeze theorem again. Therefore, what we have is, we take the limit as h and k approach 0 of 1 over the norm of hk times f of hk minus f of the origin. This is going to be the limit as h and k approach 0. We still have 1 over norm of hk. We're multiplying by, okay, so f of 0, 0 is going to be 0 by definition, and then f of hk is going to be, we're going to have h squared plus k squared times sine of 1 over the square root of h squared plus k squared. Okay, and so now this is equal to the limit as h and k go to 0 of, okay, so we've got 1 over the norm of hk. Now we're multiplying by, well, h squared plus k squared, that's the same as the norm of hk squared. Then we're multiplying by sine of, well, the square root of h squared plus k squared, that's just the norm of hk. And I've broken this absolute value up into two separate absolute values because you can do that. And now we can do some cancellation here. So this is the limit as h and k go to 0 of norm of hk times sine of 1 over norm of hk. And look, we've proven something about this. We've proven that this is 0. Thus, df at the origin is a linear function such that you plug in any x and y and you get 0. And this is because in order for this derivative to be true, it needs to be true that the limit as it needs to be true that 0 is the limit as h and k goes to 0 of f of hk minus f of 0, 0 minus df 0, 0 hk all over the norm of hk. And that's true because df 0, 0 xy is 0, and so when you evaluate this limit, you're evaluating precisely the limit that we just proved is equal to 0. And so df 0, 0 xy being equal to 0, that will satisfy, this linear function satisfies the definition of being the derivative of f at the origin. And so therefore, which means df at the origin exists. And now we need to prove again that we need to prove not only that the function at not only that the derivative f is not continuous at the origin, but that each partial derivative is not continuous at the origin. So let's do that. However, if we choose any x, y, which is not equal to the origin, then if we take d1f at x, y, this is going to be the derivative with respect to x because it's d1. I've got x squared plus y squared sine. Now, instead of doing 1 over the square root of x squared plus y squared, I'm just going to write sine of x squared plus y squared to the minus 1/2. And technically, this should be sine of this thing, so there should be another set of parentheses, but this extra set of parentheses I just wrote, I'm usually going to leave out, because I don't want to write that many parentheses. So yeah. So now we just use calculus. So this is 2x sine x squared plus y squared to the minus 1/2 plus, and now we leave x squared plus y squared. Now we take the derivative of sine, we get cosine. Now on the inside we still have x squared plus y squared to the power of minus 1/2. Then we have to multiply by the derivative of x squared plus y squared to the minus 1/2. So we bring down the minus 1/2, and then we get x squared plus y squared to the minus 3/2. But then we got to apply the chain rule again because we've still got an x on the inside here. And so we have to multiply by 2x. And so then this, we write it again. This is going to be 2x sine of x squared plus y squared to the minus 1/2 minus, we get some cancellation here. We're going to get x squared plus y squared to the minus 1/2 times x times cosine x squared plus y squared minus 1/2. Now for y equal, if we set y equal to 0, then d1 of f at x 0 is going to be, well, we just plug in y equals 0, so we get 2x times sine of x squared to the power of minus 1/2, and since we're taking positive absolute or positive square roots here, get 1 over the absolute value of x. And we're subtracting x over the norm of x times cosine of 1 over the norm of x. And so, the limit as x approaches 0 of d1 f of x 0, well, if we take the limit as x goes to 0, the 2x sine of 1 over the norm of x, that'll be fine, that'll go to 0, but this x over the norm of x, that's just going to be plus or minus 1. But cosine of 1 over the norm of x, that's going to oscillate more and more as x approaches 0. So that limit does not exist. So this entire limit does not exist. And so there exists a path upon which you can approach the origin such that the limit of d1f along this path does not exist. And so d1f cannot be continuous at the origin. And thus, d1f is discontinuous at the origin. Okay. Now by symmetry, the same thing holds for d2 of f. So if you want to take d2f of xy, it's just the derivative with respect to y. And so basically you just have the same formula for d1f of xy, but you replace all the x's with y's and vice versa. So instead of having a 2x, we'll have a 2y. Instead of having x cosine, we have y cosine. And then all the other things are the same because you have x squared plus y squared. And if you switch x and y, that's the same thing. So by symmetry, d2 f0y, we're going to get 2y sine 1 over the norm of y minus y over the norm of y cosine of 1 over the norm of y. So limit as y approaches 0 of d2 f of 0y does not exist. So d2f is discontinuous at the origin. Okay, so there we go. That finishes the exercise. And so, of course, the main point here is that just because the derivative exists does not mean that the derivative is continuous. And this is not just a phenomenon that occurs in functions from r to r. This can occur from functions from r2 to r, as we've seen. And you could easily extend, you can sort of imagine how you would extend this to like a function from Rn to r. In fact, I wonder if you had written this function in part B the way that I had mentioned, where you first have the function from Rn to r, where you just take the norm of the vector, and then you plug the norm of that vector into the function from part A. I wonder if you could write it like this and prove that prove the same thing, not just for this particular function from R2 to R, but prove it for general functions from Rn to R. But in any case, the point is differentiability does not imply, like, the existence of a derivative, and in fact the existence of a derivative everywhere does not imply continuity of that derivative. And so the idea of a function being continuously differentiable is important, and it's distinct from being differentiable. And that finishes the exercise.